When physical goods arrive faster than they can be sorted, stored, or shipped, the resulting bottleneck brings the supply chain to a halt. The loading dock quickly becomes impassable, and inbound operations collapse. A warehouse is often viewed as a static depot for idle goods, but the physical reality of high-volume logistics requires a more aggressive definition. These facilities function as active buffers. They are engineered to decouple production stages and manage the mathematical variability inherent in global supply chains. Simultaneously, these facilities serve as consolidation points. Manufacturing outputs and raw goods are routed here, so diverse orders can be assembled from thousands of distinct individual units. Because a warehouse operates as a highly active processing node, its physical layout dictates the absolute upper limits of the entire network's throughput. The central engineering challenge in any inventory facility is straightforward. You must maximize the volumetric capacity of goods stored within a strictly fixed square footage. But capacity alone is useless without selectivity, the ability to instantly locate and extract an individual unit without moving other goods. This chart shows the inverse mathematical relationship between storage density and selectivity. Increasing access to distinct items drops total capacity. On the floor, adding aisles for lifting equipment increases selectivity, but widening those aisles directly shrinks the footprint available for actual product storage. Solving this trade-off requires engineering three interlocking systems simultaneously: the physical equipment, the logical assignment algorithms, and the digital tracking architecture. Designing a layout, writing operational logic, and implementing software as separate problems results in bottlenecks. They must be engineered as a single integrated matrix. We begin with the baseline physical environment, a raw footprint prior to the installation of any racking structures or operational logic. The most basic equipment configuration is bulk storage or floor stacking. Goods are stacked directly on top of one another, forming solid blocks of inventory with zero internal aisles. This basic floor stacking configuration achieves maximum volumetric efficiency. However, because you can only retrieve the pallet on the very top or front of the stack, it is strictly limited to homogeneous, low-value, high-volume items. For mixed SKU environments, the physical architecture must evolve into pallet racking. Selective racking provides immediate, unimpeded access to every single pallet in the system. The cost is a massive penalty to volumetric density, as half of the facility's square footage is surrendered to empty aisle space. High-density systems, like pushback or drive-in racks, offer a necessary mechanical compromise. They restore significant capacity by storing pallets multiple rows deep, but reinstate strict constraints on retrieval sequencing and reduce overall throughput. In constrained urban locations or multi-story facilities where expanding outward is impossible, engineers turn to vertical densification and mezzanines to multiply the usable floor space. Vertical storage introduces hard physical limitations. Designers must carefully account for mass distribution and strict load mass constraints on the racking's deal. Placing heavy loads in the highest vertical zones creates unsafe mass distribution, heightening tipping risks. It also heavily increases the energy consumption required for specialized lifting equipment to reach those heights repeatedly. But racking systems and massive mezzanines only dictate what is structurally possible. The physical layer cannot decide where specific items should go to maximize the speed of retrieval. Stripping away the physical steel, we are left with the pure spatial logic of the warehouse floor. Every grid coordinate represents a potential storage location. SKU turnover dictates physical placement. This Pareto distribution illustrates the ABC analysis rule. Roughly 20% of goods generate 80% of movement. To optimize throughput, high-turn A items are slotted in positions that mathematically minimize travel distance. Slotting calculates the ideal distance, but it must be enforced by a storage assignment policy. The most traditional approach is dedicated storage. In a dedicated storage policy, every individual SKU has a permanently assigned fixed home on the racks. This system is highly predictable. It minimizes misplacing items, simplifying manual replenishment as workers memorize the floor plan. The critical flaw of dedicated storage is severe space underutilization. When a low-turn item goes out of stock, its dedicated slot remains entirely empty. That void cannot be used to store an unexpected overflow of a different product. To reclaim that wasted volume, engineers apply random or class-based storage. Under this logic, an incoming unit is placed into whatever physical space happens to be empty at that exact moment. Random assignment drastically improves overall density. The facility operates with nearly zero empty shelf space, maximizing volumetric capacity. Yet this creates a severe operational trap. Maximizing density through randomization creates an unpredictable map. If humans are required to search for items or memorize constantly shifting locations, pick performance collapses entirely. Executing a randomized layout using manual paper records or human memory guarantees operational chaos. The time saved by dense storage is instantly lost to endless searching. To execute random storage successfully, a digital intervention is required: automatic identification and data capture technologies, relying on barcodes, QR codes, and RFID tags. These capture technologies feed directly into a warehouse management system, or WMS. This software generates a synchronized, real-time digital twin of the physical storage matrix. When an order is placed, the WMS instantly translates the randomized storage data into an optimized point-to-point travel route for the picker, completely eliminating search time. This logic does not always demand heavy enterprise software. Even lightweight, Android-based QR applications give smaller operations immediate gains in data capture and dynamic slotting. When managers couple physical layout changes with information system support, they see measurable improvements in capacity utilization and inventory accuracy. These specific system gains are what allow a warehouse to convert a theoretical layout into actual operational throughput. Digital tracking provides the fundamental bridge that allows a facility to operate at high volumetric density without sacrificing retrieval speed. A correctly engineered architecture is measured through strict key performance indicators: storage density per cubic meter, average travel distance per pick, and the total space utilization rate. Transitioning to these metrics introduces its own operational risks. Many facilities attempt to implement digital tracking while maintaining physical paper records, creating hybrid workflows. Retaining analog records alongside a live digital twin frequently results in reconciliation errors. Without strictly designed process controls, this dual tracking leads directly to out-of-stock events and misplaced inventory. Resolving these data inconsistencies is a prerequisite for the final stage of warehouse evolution, integrating fully automated storage and retrieval systems. Before a conventional warehouse can introduce automation, it must enforce strict unit load standardization. Every item must be constrained within specific bins, cassettes, or totes. Standardizing the load carrier guarantees smooth, energy-efficient mechanical handoffs. A predictable physical form allows static shelving to interface seamlessly with automated robotic pickers and high-speed conveyors. In an automated environment, the physical laws apply even more rigidly. Vertical zoning and load mass constraints must be perfectly mapped to the precise lifting capacities of mechanical systems to prevent motor burnout and energy waste. True supply chain throughput is never solved by simply building a larger box. It requires treating the physical racking, the mathematical slotting algorithms, and the digital scanning network as a single engineered organism designed to master the physics of supply and demand.